Now we are going to define ideals in the ring. So first we will start with left ideal. So let me start left ideal. A subring L of a ring R is called left ideal if so this is left ideal if R L belongs to L for all R in R and L in L. So L should be a subring, and when you will multiply any element of R to the element of L from left side, then the resultant goes to L. If this is the property this subring has, then that subring is called left ideal. So I will come to the example, but let me on the same way define the right ideal. So Ri ideal. So a subring L of R is called right ideal if L into R belongs to L. So there is a multiplication of the ring for all R in R and L in L. This is left ideal, this is right ideal, and now we have two-sided ideal. And in short it is also called ideal. So whenever I will say ideal, ideal means two-sided ideal. So what is two-sided ideal? A subring L of R is called two-sided ideal if L is A and L is a left ideal and B a right ideal. So if L is both ideal, left ideal and right ideal, then it is called two-sided ideal or ideal, simply ideal. So before coming to the examples of this two-sided ideal, let us see how to test whether a given subring or given a subset is an ideal or not. So test for ideal. So suppose A is a subset of the ring R, then A is left, and in bracket I am writing right ideal if and only if number 1, A should be non-empty. Of course, because it is a subring also, so it should be non-empty, and because A has to be a subgroup for being a subring. With respect to addition, A has to be a subgroup. So let me write the condition for subgroup test. AB in A should implies A minus B belongs to A. So in this way A plus is now subgroup. By these two conditions A plus is a subgroup. Third condition. So A dot should be a semigroup. So if we take two elements A, B in A, that should implies A into B should be in A. That is a condition for semigroup. But what we want it to be an ideal. It means not only the elements of the product of elements of A should be in A, but also if we take one element from R and one element from A, their product should be inside it. So it means for R in R and A in A, this should implies R into A should be in A, and this is a condition for left ideal, and I am writing for right ideal in bracket A into R is in A. So if this condition hold, then we say the subset A is an ideal. So this is the test for ideal. And what about for both sided ideal? If both the conditions are true, then it is both sided ideal. So let us see it by example. So one of very easy example is the trivial subring. So let me come to an example. Take A to be the zeros subring. This R is a ring, and now you can see that A is non-empty. Of course AB belongs to A, then A minus B is in A. A has only one element 0, so it will always happen. And now take any element R in R, and you have only one element, then R into 0 or 0 into R is 0, so that belongs to A. So actually A is left ideal and also a right ideal. So A is both sided, two-sided ideal, so A is an ideal. Ideal called zero ideal or trivial ideal. This is called trivial ideal. So if I am saying that non-trivial ideal means that ideal is not equal to 0. So this is called trivial ideal. So another example, take A to be the whole ring. It will satisfy all this property because it is non-empty. AB is in R, then A minus B is in R because R is plus is a group, and because R dot is a semi group. So if you take two elements, both are from R, so their multiplication will be in R. So it is also an R is an ideal. That is it. Two-sided ideal. This is called, and it is called improper ideal. Improper ideal. So what is proper ideal? An ideal which is not equal to R is called proper ideal. So by proper ideal mean an ideal I not equal to R is called proper ideal. So these two ideals will always be there in any ring. There is no problem. These two ideals will always be there in any ring. Now, Another example, take ring to be Z set of integers, and we know its subrings are of the form mz. So take a subring a mz and let us check whether it is an ideal or not. So let us check. First condition, of course a is non-empty, a is not equal to 5. Second condition, so take two elements from this ring. So mz1 I take one element and mz2 I take another element, and this implies mz1 minus mz2. So this is mz1 minus z2, where z1 and z2 are integers. So z1 minus z2 is also an integer, and we have multiplied by m, so it is of the form this, so this belongs to mz. So second condition is satisfied. And now what about third condition? So let us come to the third condition. So take one integer, so I take one integer z in z, and I take mz1 one element in mz. And what about their product? So let us take their product z mz1, that can be written as m times z z1. So either you multiply from this side or you multiply from this side, you will get the same result. So both the conditions are satisfied. So it is left ideal as well as right ideal also. So it is an ideal. So this is an example of ideal. So it means all the subrings, we know that all the subgroups of Z are of the form mz, all the subrings of Z are of the form mz, and now all of these subrings are actually ideal. So now come to another example. Now before coming to the example, let me write one thing. Note that if R is commutative, then left ideal, right ideal, and ideal are same, because the ring is commutative. So this condition R into A, if you will take, or A into R, both are same. So it is left ideal, right ideal, these things are same thing, and because they are same, so every left ideal is a right ideal and right ideal is a left ideal, so every left or right ideal is an ideal. So this was one remark. Let us come to another example. Now example, suppose I take R to be the 2 cross 2 ring integral matrices. 2 cross 2 integral matrices, the set of this 2 cross 2 integral matrices forms a ring. So I take this ring, and now let me take one subset A1. I take one subset, and that subset is suppose I take 0 0 AB such that AB belongs to Z. So let us check whether it is a left ideal or right ideal, or it is ideal. So now it is clear that A1 is not equal to 5, A1 is non-empty, and let me come to second condition. So take two elements of this set 0 0 A1 B1, where A1 B1 are integers, and I take another element 0 0 A2 B2 in A. So I take two elements in the set A. Now this implies what is their difference? So their difference, if we will take 0 0 a1 b1 minus 0 0 a2 b2. So by the definition of addition of matrices, we can write it as 0 0 a1 minus a2 and b1 minus b2. So as you can see that this is again an integer, a1 minus a2 and b1 minus b2, and first row is 0, so this element will belongs to the set a1. So the second is satisfied, second condition is satisfied. Now come to the third one. So third condition is, so let us see 0 0 a1 b1. So let me verify third one. This in A I have taken, and take another element from the ring. So let me take A, B, C, D is another element in the ring R, which is equal to the 2 cross 2 matrices over Z. So now what does it implies? Let us multiply 0 0 a1 b1 and a b c d, and let us see what will happen. So it will turns out to be 0 0 and second row, so this is a1 plus b1c, so 0 let me write here, and this is a1b plus b1d. So this is again of this form. As you can see that it is of this form. So because it is of this form, so this belongs to a1. So now here this element is on right side, left side, so it is a right ideal. So this implies a1 is right ideal of R. So this is an example of a right ideal. Now one thing you can see that if you will multiply it from the left side, so you keep it in left, then what will happen? So a1 b1, it will not be equal to a matrix of the form 0 0 and some integers. So you can multiply and check it, because it is not of this form always, so it is not a left ideal. Now I am giving you as exercise to verify one more example, and now on the same ring I am giving you another subset A2 to be 0 0 AB, such that AB belongs to Z, and the exercise is verify that A2 is left ideal but not right ideal. Let me give you one more exercise on the same ring. So take A3 to be 2A, 2B, 2C, 2D, such that A, B, C, D belongs to Z. Verify that A3 is an ideal of M2 cross 2 Z. Now come to another example. Suppose R is a ring. I am not saying commutative, just ring, and take a non-zero element A in R. Take a non-zero element in R. Then define a set so let me define a set. We will denote this set as AR. Just we have multiplied all elements of R from A from the left side. So this is AR such that R belongs to R. This is the set. So the question is it an ideal? So this set is non-empty. Why? Because for some element of R, when you will multiply it with A, you will get at least some elements. Note one thing, that if R does not have identity element, then A will not belongs to it. A may not belongs to it if R has no identity element. So first thing, this AR is non-empty. Why? Because at least 0 is there in R. 0 into A if you will do, you will get 0. So 0 belongs to AR. So this is non-empty because at least 0 belongs to this set. Now take two elements of this set. Take A R1 and A R2 in this AR. Then what will happen? What about the difference? A R1 minus A R2. This is A R1 minus R2. Because R is a ring, so R1 minus R2 belongs to R. So it is again of this form. So this belongs to AR. So second condition of this test is satisfied. Now come to the third one. Third condition is that, so take an element R in R. So I take an element R in R and I take AR in AR. So what will happen? AR into R. So let me take R1 here. R1 into R if we will take, then it is A times R1 R. R1 R is again an element of the ring. So this is again of this form AR. So this belongs to AR. So as you can see that when we are multiplying the element of the ring from right side, then it belongs to A, so it is an right ideal. So AR is right ideal. This is right ideal. Now similarly, I am giving it as exercise. Verify that RA, which is R into A, such that R belongs to R, is a left ideal. Is a left ideal. Now note one thing, that if R has no identity element, then what may happen is that A may not belongs to AR and A may not belongs to RA. Okay, if R does not have identity element, because if R has identity element, then A can be written as A into 1 or 1 into A. So it will obviously go to this set, but if R does not have identity element, that these two ideals may not contain A itself. Now let me give you some more example. So let me write exercise in place of example. So consider again a ring R and take an element A in R and take a set A1 to be AR plus NR such that R is in R, A is fixed and N belongs to Z. So this is one set. Verify that so this is our right ideal. A1 is right ideal. Let me make a correction. This is A. This is the right ideal. And similarly define another set A2 to be RA plus NA such that R is in R and N is in Z, and show that or verify that A2 is left ideal. A2 is left ideal. And one thing you can observe that A, because this is n into A and n is an integer, and so A into 0 plus 1 into A you can write. So this belongs to A1, and 0 into A plus 1 into A you can write, so it also belongs to A1. So this both the set contains A also. So these are the left or right ideals which contains A, even if a ring has no multiplicative identity. Even then both the sets contain this ideal. One more remark I would like to give you. Suppose R is a ring with identity, then verify that AR is same as A1 and RA is same as A2. So both are same thing. Okay. One more thing. Let me give you as exercise. Suppose R is a ring with identity. R is with identity, and I is an ideal. It may be left or right also, there is no problem, left or right also. Then what will happen is that suppose 1 belongs to I, then I will become equal to R. So just verify it, very easy to verify it. So I am leaving it as exercise for you, so do it.